one different marker. So there's plenty of markers, so we'll identify them. So, function of the economy, we are thinking about it like class. Depends on variables. So we'll define t times a, q times a. This was a series of designs. So first there's some prefactor, which let's not worry about prefactors. Times summation d z the d, and now this q hypergeometric equation underlines what it is. So d ta t is q factorial d, where t sub d means 1 minus t, 1 minus t, 1 minus t. So this interesting function solves a Q difference equation in a second order Q difference equation in every variable that you see here on the board. But interesting feature of that was that the equation in Z and the equation in A are the same equation. So and also for those of you more conventionally minded, discussed yesterday, the determinating cases of this. So how can I make this series terminate if I make this t times, if I choose A so that t times A is q to some negative power, and this series terminates, and that would be a McDonald's type A1, the corresponding degree. Okay? So now we will try to look at some more. I don't want to repeat the whole lecture, but now we'll try to look at some of the properties of this function and some of the phenomena associated to that from the point of view of more slightly geometric view. So how are we supposed to think about things like this? Geometrically, is first what are they? So there's 4 variables here, and there's 4 tuples Z, A, T, Q. Well, for us, well, they're non-zero complex numbers, 4 tuples. But we will think of this as this thing as a group according to by multiplication. It's clearly the multiplicative structure is very important in writing the number. It's a group. And what this expression will be, this will be a trace of this element, which is 4 tuple, the Q, in some representation of this. In the notion, we study in many mathematics. People look at representation of a group, that is to say, a group element like a matrix, and you take the trace of this matrix in this representation. Of course, this representation, since it's not, if it were a finite dimensional representation, that would be a polynomial. So if I take finite dimension, so what does it mean a finite dimensional representation? The finite dimensional representation, what are the representations? The representations, they're irreducible, they're all one-dimensional, and just say this 4 tuple just goes to some monomial. Just to some power, A to some power, T to some power, Q to some power. every representation being for this group is a sum of irreducible representation. If we're a 5-dimensional representation, it's just sum of monomials, which this expression isn't. But this expression I can certainly expand in a series in which I have monomials with integer coefficients, and some, I should say, maybe virtual representation. Yes, to chase an actual representation. Chase an actual representation has to be some of monomials with positive coefficients. If I expand this in a series, well, you see that you see constraints with sign, and so this means it's not it's a difference between two representations. The trace in one representation minus the trace in two. Make sense? And so then when we talk about this kind of expression, maybe the first thing to discuss is some representation. This is the representation constructed genetically. So what's the simplest possible instance of what I have several matrix of the form, let's call it A1, A2, a matrix. All this acts space. Of course, the trace of this matrix in this representation is just A1 plus A2. But it also acts on functions. See, there will be a infinite dimensional representation. And what would be so the trace here equals A1 plus A2. I don't need to insult your intelligence, but if I look at functions of C2, what's it going to be? So this means this is the span of all monomials x1 to some power m1, x2 to some power m2. And each of these monomials is an eigenfunction of this matrix. The eigenvalue for each of them is each of these is each one is an each one is an okay, good. It's eigenfunction with eigenvalue. This is my favorite question for students when they come to study representation theory. This sort of question: what is the eigenvalue of this element under the action of F matrix? And to make it life easier for you, it's not really important for the subject of this talk, but just to make sure we somehow understand what's happening, I'll write an answer which is incorrect, and then somebody should point out that why is it incorrect if I write A1 to the power M1, A2 to the power M2. It's incorrect. Right. It should be minus, because I think I explained to students that in linear algebra they tell you that all vector spaces of given dimensions are isomorphic, which is maybe true in linear algebra, but in representation theory and other parts of mathematics, you should be really cognizant of the fact that the representation is not the same as the dual representation, and the vector bundle is not the same as the vector bundle. So it's a dual vector bundle. So if my element acts in a representation by a matrix like this, it acts in the dual representation on functions. It acts, well, in general by transpose. It has to act by A1 inverse A2 inverse transpose, well, the transpose is going to be the same, but in general, that's how I can do representation. So it's minus. And so then if I take the trace, I have to sum it all M1 and M2, and so then the trace of in functions C2 of the matrix A1, A2 is equal 1 over 1 minus A1 inverse 1 minus A2. Product of two geometric progressions. And so this is already, and it's clear that if instead of two-dimensional space I had a higher dimensional space, I would have things like this. So this is if I want to produce a denominator of this kind, and well, get something of degree 2D, so it means I'm going to be acting somehow in 2D dimensional space. I'll get some expression like that. Now, what about the numerator? So the numerator is maybe like, again, so let me maybe argue it like this. So this is my coordinates, x1, x2. And if instead inside of all functions, I impose equation that x2 equals 0. I impose equation x2 equals 0, that means I mod out, in other words, I mod out by all functions that contain x2. So then, of course, in this new trace, of course, should be, I compute the trace. The trace should be just, of course, 1 minus A1 inverse, because now it's just, there's no A2, like there's no x2, right? But the way you think of it, I first had functions of two variables, and now I impose equations. Then, well, you should think of this as first I had all functions, and now I put the numerator like so. This numerator is responsible for this equation. So things in the imposing equation means modding out by all functions that contain x2. You can write some kind of exact sequence, which people would call Kazoo complex in this instance, and that has the effect of bringing a numerator. If a numerator I can get from things that I impose some equation. Like for instance, if I want to know the characters, instead of imposing equation for x1, I just set x2 to 0. What if I impose equation that the product of the two is equal to 0? If I impose equation x1, x2 equals 0. I take functions on the union of two coordinate axes. That's what the function we use. The function on one axis, the function on the other axis have to take the same value at the origin. And so you can easily convince yourself that this character is given 1 minus the take all functions. And then what is this has eigenvalue of this kind? This has eigenvalue of A1 inverse, A2 inverse. So we have to put 1 minus A1 inverse. And you can easily check that it's correct. Where does this fit? Where does this whole thing fit? Is that in general, so if I have some group, with some G-algebraic group, and then this which operates on some x variety, And then it's meaningful to ask what was the trace of G acting on functions on X. We'll say that doesn't right? That would be in general an infinite dimensional representation, and what this is, if first in our case the varieties with standards are very simple, they're just coordinate spaces or the equation x1 equals x1 x equals 0. But in general, you can have an interesting algebraic variety. And so these the functions. What are the functions? Functions, I may say so. These are the global sections of the ring of functions on X. There's a notion of the sheaf of functions X. For every algebraic variety, it comes with the notion some coordinate charts, I have some sort of functions, and then I take the global sections of this object. And of course, you might as well, instead of this, replace by a vector bundle with an action of G or more general shape. So vector functions need not be scalar valid, they can be valid in some vector space, and that vector space may vary with the point in X, and then replace this 0 by some kind of hierarchy homology. So you get many, if I have an action of a group element on some algebraic variety, I have many ways to construct representation, which in general may be infinite dimensional, but they will have very often very well-defined traits of elements. And there is very nice calculus. There's a particular nice calculus. For something called Euler characteristic. Namely, when you take the Euler characteristic of some, let's say we have a vector function. People familiar with sheaves can only substitute vector bundle but some kind of vector bundle. This is the alternating sum. You compute the trace of G acting in the K homology. This is some essentially topological quantity, like an index of an operator. And this is the particularly nice rules to compute that. And you see that these expressions are naturally have signs in them, and which is now why you would naturally have, if you expand out an expression like this, you will naturally have some kind of every power of t would have with its own sign, which is the kth power of t will come with its sign minus 1. So this is the subject. Thank you. Euler characteristic for natural. Well, all right, see. On there's moduli space. A particular kind of moduli spaces that's relevant to expressions like this. In particular, like in particular, we study, maybe let me not be too specific, just study moduli spaces of maps of some, let's say, for the sake of argument, let's say P1. Some. Now, we previously had X was an algebraic variety in which the group was acting, but now there will be maps to an algebraic variety in which the group is acting. And here, this thing here, your group element G to action, and this G will be an example of that. G will be our TA. Okay? This TR will be acting on X. What will Q do? Q will just act on natural act on Q1. So this would be just they take and there's an action of GL1 on C. GL1C acts on C and acts on P1. And then finally what will Z do is that this space of maps is written in some infinite. It's not only so we previously were getting infinite dimensional representations from finite dimensional algebraic variety. If you look at things like this, well, this would be of course speaking infinite dimensional algebraic variety, but it's a union of finite dimensional ones, namely you fix the degree. So if you fix a map of a P1 some algebraic a curve, this is the image of that as a curve in X. And this has a degree, namely, for instance, if X sits in some ambient projective space, that means this would be given by polynomial of a certain degree. And if I fix the degree, that's a finite dimensional algebraic variety. And so this is a union of finite dimensional algebraic variety. And so if I compute the Euler characteristic of anything at all, this would be naturally graded by this degree here. Degree, so it's a direct sum of finite, direct sum of representation. This whole thing is compute functions on a union of things. This is naturally graded by what indexes this union. The D is that Z to the D. This is Z to the D is just saying my D is graded, but the eigenvalue of Z to the D corresponds to map. That's where we go. Okay. And why? How you can, so maybe before we plunge into any further depth, let me advertise what could possibly be advantage of studying things like that. So okay. In the end, we were interested in some combinatorial, maybe analytic properties of this function. So how can any geometric consideration help with any sort of analytic property? So just write it like this. Now we take output. This sort of consideration. The basic one is the following. So we remember we had the let me write this. So let me recall what we had here. What we had here was the trace in functions. All right, functions on. All right, let's say so that's not confuse people. Let's write the two-dimensional coordinate space is A2, or you prefer the two-dimensional coordinate space C2 or A2? Which one is? R. that yeah, this is that you see the
So A2 is.
A2 is fine. Well, okay, let's take C2. Because what if we get to the adults later? So this is all of the matrix A1, A2. This has the expression 1 minus A1 inverse 1 minus A. Again, not to insult your intelligence, but this is a basic feature of this formula is that this has poles. Just written there, and has has poles. Where does it have poles? It has poles when one of A1 or A2 is equal to 1. And what does it mean? That means it has poles. Let's take this element G, call it G. When is the, so maybe I'll write it, but I write X here, and then my X would be C2. This has poles when one of these guys is equal to 1. And the way to say it is that poles when does it have poles? When I look at the fixed locus of my transformation. If one of these eigenvalues is 1, then the fixed locus is either all of x or one of the x is not compact. So I have a transformation. I look at the fixed locus of that transformation. This could be an axis, whole thing, or the origin. And if it's not the origin, if it's an axis or the whole thing, that means it's not compact, then this has a pole. And this is completely general statement. If I compute the Euler characteristic of some kind of on some sort of x of some kind of sheaf, so this is I compute the trace of G in this fashion. This has a pole. If this thing has a pole, then this means that if I take the fixed locus G intersect with the support. So in general, this sheaf by itself. So sheaf is something. It's like a vector bundle, except its fibers, can jump. It could be like, for instance, it could have a fiber at a point and no fiber at any other point. So when I take the support of that sheaf, it is not compact. In other words, if it is the case that the support of F intersects the fixed locus, in a compact set, then this thing has no, this thing is empty. And if I may remind you what we were doing, we were 4 equations like this, the basic analytic question that we discussed yesterday is that this function here has sibling function in which it's also the same, where I exchange the roles of A and Z. This function, the miraculous property of this function, that it was solving the same equation in Z and in A. So in particular, I can take this formula and exchange the roles of A and Z. And this, if the series was terminating, that's actual symmetry. If the series was not terminating, that is not the same function. Because, for instance, has poles, somehow poles in different locations. And so then what we're talking about that is all essential information about the function, the equation, everything is in fact captured in the transformation from phi to this. If you know how to go from phi to the one where you exchange these variables, that in some sense captures all essential information. But that transformation is really about canceling poles in some expression. Right? So here this has no poles in Z and some poles in A. So if I'm looking for some transformation from the elliptic matrix that takes this and produces that, and it's a question of being able to cancel poles. That makes sense? And if you eyeball some combinatorial expression, trying to determine whether poles cancel or not, this can be arbitrarily complicated. And this kind of argument is the best way known to me. And I thought about this for a long time. So probably the best way. But actually, if somebody gives you a complicated expression, tells you proof by some kind of argument that it has no poles, that in fact that's the only kind of argument I know how to do. That's by far the most popular, the most powerful thing to check, because we're in this lecture series we're progressing slowly. We somehow looked at maybe the simplest possible function I can write on the board, and anybody who ever really plunges into combinatorial complexity of the kind of function wants to start generalizing, you know, it's not, you can appreciate the difficulty of trying to prove something has no poles without some geometry. And funny enough, I've been in some other line of work, I've been the one who's doing this Kazan, I've been involved into another funny application of the same principle. Namely, that has to do with spectral theory. So, for those of you who know the old spectral theory, if I have a pole in the resolvent, means I have a point in the discrete spectrum of some kind. And so if I have in spectral analysis on some automorphic forms, it's the idea, this sort of argument about match poles to some non-compact, make some expression and break it up so that you understand where all the poles are. That's actually kind of it's another application of this thing. Okay. So now,
in the general case of G acting on X,
yeah,
this has to do with closed orbits in the projective space of X. That this happens if and only if the orbit is not closed in the projective.
It's not so much with the orbit. It's really the fixed loop.
Okay.
Yeah. So it's somehow you have to. So there's anytime you have a group acting on X, there's the interesting algebraic variety, namely the group element and its fixed locus, and that's that tells you in the group, that tells you all the possible. It's an interesting thing to see. Like in the group in particular, you can look at the locus where that fixed locus is not compact. That's where you expect it. So now we need to somehow bring it closer. So what about this expression here? Or why do I say that we need to talk about math? Let's remind ourselves another object we've seen yesterday, namely the Okounkov function. This object here, this Bahammer symbol, is the ratio to Q-gamma function. We should talk about the Q-gamma function. That's the 1 over A. That's right. Thank you for that. This is where can we realize this object in the story I'm talking about? Well, this is clearly the trace of the element on where functions on functions. Well, this is if I had two terms there, this means I have a two-dimensional space. So we have infinitely many terms on an infinite on functions on an infinite dimensional space. Already, these are functions on an infinite dimensional space. What do we know about this infinite dimensional space? On this infinite dimensional space, my element A and Q has to act with eigenvalues. Well, the eigenvalue is the inverses of what I see here. So it has to act by a matrix A inverse Q inverse A inverse Q A inverse. Now, when I compute, I need to take it, like, call this infinite dimensional space M, anticipating its interpretation. Now, what if I take the trace of this one, so functions of M, this would be C of M. And if I compute the trace of A and Q acting on just M itself, I'll have to sum up all these things. What's it going to be? It's going to be A inverse times the geometric series. So M itself looks like a space of function. Make sense? This already looks like a space of function. Namely, This is in fact what this is the space of math from space of math from where? From a line C1 to a line C1 where I have my so I have a space of math from a line to a line, so that's what we all possible yeah, right? Where so this would be the span of a constant function x, function x squared, function x cubed, and so forth. And now I will make my group act like this. I will make the group act by multiplication by q in the source of this function and multiplication by a inverse in the target. Well, how would that affect the minimum? So maybe the easiest with a constant. So if I have a constant now, constant with some value, well, on the space of constant, ax by just scales that constant. On this thing, I get an ideal value. A inverse. On x, how does in general how do I act? How does an element act on a function? So if I want a group acting, so let's just write the general formula. If I have a function and I have an action in the source and the target of this function, what am I supposed to do? Under the action of A and Q. So A acts on the source, so it's post compose. So A inverse here, so this would be in the domain, in the target of the function, I just multiply by whatever I have to multiply. Then I take the function, and then in the domain I have to act by the inverse. So it has and so this means I get my this will have if f is constant, just get me multiplied by a inverse. If it's x, it's going to be a inverse q inverse. If it's x squared, it will be a inverse q minus 2 and so forth. So the space of functions has the character I wanted. So if I study the space of functions on the space of functions, I get this q value. And then if I want some sort of truncation of this q gamma function, and this is even easier. If I want an expression of the kind 1 over, let's say, well, let's not put q. Let's have a e. This is well. Try it out. Q minus 1. This is the trace. on the subspace here on polynomials, on the space of polynomials. So this is, instead of all possible monomials, I only allow up to d minus 1, so the space on the span f of x equals 1x, x d minus 1, and so this means polynomials of degree t, d minus t const. If I impose a degree condition, then I get this truncate. So finally, let me try to since we were talking about this particular function, let's just so I will be consider static maps from P1 to C star P1. So this will be my x. Which are, so inside here, I look at the space of how, first of all, how am I supposed to think of a map like that? So a map like that is, first of all, what's a map from P1 to P1? So a map to P1 in homogeneous coordinates, it means I have two polynomials of some degree. And so this is, so first think about P1 to P1. The locus I want to look at consists, the first coordinate will have x to the t plus some polynomial, something of degree maybe I write it f1 of x, maybe called 1 of x, where this x, the degree of this f1 of x is less than d. This is a fix, and then the other homogeneous coordinate would be just f2 of x. The degree of this guy will be also similar to degree which is less than d. In other words, when I think of maps to P1, then I fix the value for x and infinity. I fix the value to be 1 and 0. So this means if x equals infinity in this P1, I want the value that x to infinity is mapped to the point 1. And then if I have a degree D map, so the neighborhood of this degree D map, it means I will perturb it by a map of degree less than D, And if I make my A, I would like me to scale this coordinate by A. Instead, it's a homogeneous coordinate. If I scale this coordinate by A, I might as well scale this coordinate by A inverse. So I have two polynomials of degree, both degree less than D. One is just, here I just scale my x. My x is always scaled by Q. And my target is, in principle, I'd like it to scale by this matrix, but in homogeneous coordinates, it does the same as scaling by this matrix. Scale the second coordinate in, and so I'm getting from this. The pairs of polynomials, it's a vector space, and the coordinate of and the character of that vector space is this. And the numerator that comes from the. So if I'd like to somehow write things for the cotangent direction, the cotangent directions will have to be given, the map to cotangent directions will have to be given by polynomials of degree minus. There's none such, and so it's like that this is the fact that instead of they had this discussion how variables give you denominators, equations give you numerators, and so this is the cotangent direction they give you. This t acts quite literally just scaling the cotangent directions and the cotangent directions together. And this is okay. Now you can imagine there's many setups you can study like that, and there is a general very interesting idea. Idea is that of something called 3D inverse symmetry. And it says about there exist pairs of dual varieties. Pairs of dual varieties. For which this kind of function phi variables that we just wrote it in z a and then t q, where this is the role of z is keeps track degree of a x number of x on x pairs and these are both symplectic Poisson varieties. This is actually preserving Poisson form. And this thing scales so this, the cotangent bundle do something if I scale just the cotangent direction that scales the symplectic form. In general, T is the weight of the symplectic form, or inverse to the weight of Poisson form. This is for x. That is really solves, it's not equal, but solves the same equation. As in all variables that f. And the example that you may want to check. Okay, I was planning to do it in the lecture, but I'm running out of time. So this is exercise. Exercise. Check the simplest instance of that, when x is t star p 0 and x check is just c2. And what is that supposed to be t star p0? T star p0. Well, okay, we're out of time, so I don't want to discuss why this is the right answer. But if this was the story for p1, then for p0 you just have to remove the second part. And so that means from this expression you just remove this part. And then what are you going to get? You're going to get a q-binomial theorem. So you can apply your q-binomial theorem and see that that works out. So, and the key object is the transition metric. This is what connects. It's what connects this and that. So this is between. So they solve the same equation without being the same function. So that means between them there's some kind of transition matrix, which is a matrix of the function. And this matrix of elliptic functions is interpreted as is in fact some unique. Elliptic. So this is the story we were talking about now. It was about traces of subgroup elements acting in some vector spaces associated with algebraic variety. You think this Euler characteristic? This is some. I said we're going to compute Euler characteristics. Euler characteristics means we go to something called K theory of that corresponding algebra, and that just K0. So this is and once, but beyond K theory, there's some geometric object in which elliptic functions of your parameters in the group live. You take your group and you mod out by what we started with something in a torus, but if we have something periodic, means we took our torus and we modded it out by take a torus and we can mod it out by q to the z. This is an elliptic curve. And there's some geometric theory that instead of taking variables here, takes variables there, called elliptic homology. And in particular, there's the objects of elliptic homology naturally produce elliptic things of picked up to the right side. And the kind of beauty of what we have now, I don't really have to stop. Maybe I'll say two things about this guy. So one, it's like a Fourier. It's like in this story. So you think of this as being some kind of non-abelian generalization of Fourier transform. That's like the analog of that Fourier transform there. And second, the variable z, in the beauty of that story, the variable z here. Anytime we have in unitary geometry, we're struggling to say something global about the generating function. Here, okay, that's a hypergenerating function. But in general, we're counting things in various degrees, and then somehow some series in Z, and that Z is just a formal parameter, which somehow we don't have so much control over that. In this language, there's no curves, there's no curve counting, no nothing. It's just there's a very special elliptic class that for the case for simple, this is like an analog of Poincare line boundary. There's something which is not okay. Well, anyhow, I apologize. There are quite a few things I wanted to say, but there's always well, even bad things that have to come to an end, and good things too. And so this is these are I have to stop on that. Just thank you so much.